Hi everyone, thanks for coming. I'm Paul Zhang, graduate student at MIT, and I'd like to share with you some work we've been doing on computation of crossfields. The structure of this talk will be as follows. First, I'll define a crossfield and demonstrate its usefulness in a variety of ways. Then I'll show that despite the widespread use of crossfields already, that existing crossfield methods are still insufficient for certain purposes, namely feature alignment. I'll go into detail about our new algorithm for computing crossfields and how it relates to previous methods. And finally, I'll show how our method solves the feature-aligned crossfields problem. The core of this project is about construction of crossfields, which is an assignment of a cross to every point in a domain. For example, at every point on this arch, a cross is visualized in blue. You can also get a crossfield on surfaces in 3D, and in this case you get an extra constraint that the cross needs to lie in the tangent space of the domain. A slightly mathier definition is to say that a crossfield is a map F from the domain omega into the space of crosses. And they appear in a variety of situations. For example, in this work, a crossfield is computed on various curved surfaces to guide the layout of where you would punch holes for the design of curved breadboards. This allows you to thread electronics into all sorts of objects. In this work, a crossfield is used as part of a fabrication pipeline for complex shapes. You can trace streamlines of the crossfield, and these tell you how to approximate your shape with a bunch of planar wooden strips. Maybe in a more culinary or artistic application, you could use them to design interesting weave patterns over the surface of a pie. These examples were all made by members of the GDP group at MIT, which surprisingly does not stand for geometrically designed pies. It stands for geometric data processing. And maybe the most common application I've seen crossfields used in is for quad remeshing, where you start with an underlying triangle mesh, you compute a crossfield over it, and you use that crossfield to guide the layout of quad faces over the surface. And so there are a lot of existing crossfield algorithms out there that suit various needs, but there are still certain applications for which existing crossfield algorithms are insufficient. For example, consider the following shape. And let's say you wanted to create a quad mesh of this shape. So you start with your triangle mesh, compute a crossfield using any of the existing methods, and then use that to guide the layout of a quad mesh. Now there's a problem, which is that the sharp features of the original domain have been paved away by the quad faces. It almost looks like it's been aliased. The reason this happens is because existing crossfield methods are either intrinsic or extrinsic curvature aligning. The extrinsic curvature directions are visualized in blue on the left. You can see that they are 45 degrees offset from the feature curves, which are the sharp creases of the surface. In contrast, we have a new algorithm for computing crossfields that are feature aligning, which results in very different crossfields from the top row. And if you use that to create a quad mesh, you get a much more faithful representation of the domain. I should mention that this can be done without explicitly computing what the feature curves are, because while this domain is meshed pretty nicely, if you have triangle meshes of an arbitrary domain, various sources of noise make it fairly hard to know what is and what isn't a feature curve explicitly. So the goal of our project is to compute feature-aligned crossfields without relying on explicit feature curve extraction. Now let's see how to do that. The way we achieve this is through a crossfield optimization with a novel representation of crosses and a new energy functional. Since all previous crossfield algorithms are also optimizations of some form, I'll try to present a very general framework and place several previous works in reference to it. The steps to computing a crossfield consist of first, choosing a representation for the space of crosses. Some examples from previous works are a vector per face, vectors per vertex, angles per edge. All of these would be different representations of crossfields. In our case, these are going to be spherical harmonic functions on triangle faces. And by choosing a representation, this usually implies the form of your tangency constraints and your non-triviality constraint. The tangency constraint makes sure your cross lies in the tangent space of the domain, and the non-triviality constraint makes sure your solution isn't just entirely zero, which would be pretty boring. Step 2 is to choose the energy functional, and this is the more creative aspect of it, where you really just think about what you want the cross-field to achieve for you, and you design an energy that achieves that goal. And step 3 is to either relax or to get rid of the non-triviality constraint. This is a pretty commonly used strategy because it often happens that if you relax or remove this constraint, then your optimization becomes convex. For example, if the tangency constraint is linear and the energy functional is convex, then you could solve this whole problem to global optimality. So we essentially just follow this recipe, which summarizes our algorithm as a choice of representation and energy. And before I go into detail about what our representation, constraints, and energy choices are exactly, I just want to give a high-level view of cross-field optimization. It turns out that a lot of previous cross-field algorithms also follow this recipe. This is nowhere near an exhaustive list, but you can see the breadth of different algorithms that output cross-fields of differing properties. So now we're going to tunnel down into the details, starting with step 1, choosing a representation. What we did was we started with crosses as unordered pairs of orthonormal vectors in a tangent plane, added to that pair the normal direction, so now you have an unordered triple of orthonormal vectors, which happens to be called an octahedral frame because of octahedral symmetry, which we'll talk more about later. And then we represent the octahedral frame using a spherical harmonic function. The spherical harmonic representation of the octahedral frame is essentially a function plotted over the sphere that has 6 peaks, where each of the peaks are in one of the directions of the octahedral frame. And those peaks are visualized as yellow spots on the right. So this encodes the octahedral frame, which encodes the cross, and so we have a spherical harmonic representation of a cross. I should mention that the spherical harmonic representation of an octahedral frame was first used by Zhang et al. In 2011, but this is the first method to use it for computing cross-fields. The reason this is a nice representation in comparison to maybe a more naive representation is because if you were to use something like triplets of vectors visualized on the top row, what you would get is that a lot of triplets of vectors that represent the same octahedral frame are not equivalent in their representation. If you convert them into their spherical harmonic representations, then you'd see that they're all actually equivalent. Another nice property of this representation is that it's isometric to the space of octahedral frames. More concretely, we express the representation using the fourth band of spherical harmonic functions. There are exactly 9 fourth band spherical harmonic basis functions, pictured as the blue-green shapes. So if you wanted the spherical harmonic representation of the XYZ axis aligned frame, you get the corresponding 9 vector. So now we've chosen a representation for crosses. We can say that what we're after is a map from the domain into R9, and this implies the form of the tangency constraints and the non-triviality constraints, which I'll get into next. So for simplicity, let's consider just the z-axis aligned frame pictured on the left, meaning the tangent space is the xy plane. Let's say that it's rotated in the z-axis by an angle theta. Then the corresponding spherical harmonic representation is given by this equation. From an optimization perspective, this means there are 7 linear equality constraints and 1 quadratic norm constraint, meaning if you have a 9 vector and you impose these linear and quadratic constraints, then you are guaranteed that this 9 vector represents a z-axis aligned octahedral frame. Well, what about arbitrary normal directions then, where the tangent space isn't just the xy plane? The way to represent this constraint is to first rotate your spherical function so that instead of normal alignment, it is z-aligned. Then you can just impose the z-alignment constraints on the rotated frame. But I haven't yet explained how you rotate a spherical function. It turns out that that's not much different from how you would rotate a vector in 3D. So let's say you have an axis angle rotation v. The way you would compute the rotation matrix form of it is to use this equation, which is exactly equivalent to the more familiar Rodriguez rotation formula. So that's how you would rotate things in 3D. The way you rotate spherical functions is via basically the same exact equation, except now you can call it a Wigner rotation matrix. The only difference between these two equations is in the choice of what constant sparse matrices A and B are. From a user's point of view, it really doesn't matter. You can download these matrices or compute them in Mathematica and just use them. From a more theoretical point of view, there are different representations of the same space, that is little SO3. And so now, if you have an octahedral frame and you want to rotate it by a rotation matrix RV, you could convert that into an axis angle rotation, then use this exponential formula to obtain the Wigner rotation and apply that to the spherical representation. Okay, so now we have the form of the tangency constraint and the non-triviality constraint, which is just the linear constraint described earlier and the quadratic norm constraint. And the next step is to choose an energy functional. There are a lot of possible choices here, and I'll go over a class of energies you could use, but before I get to that, I'm going to quickly remove the quadratic norm constraint. The reason you have a non-triviality constraint to begin with is to make sure that your solution is not identically zero. It turns out that the linear constraint is enough to guarantee your solution is non-zero, in which case we don't need the quadratic norm constraint anymore. Doing this transforms the problem into a convex optimization if the energy functional is convex, and for the next couple energy functionals, they will be convex. Going back to the outline, we're around here. For the first energy functional, we'll start with a very common choice, the Dirichlet energy, and from there, if we take the square in the integrand and remove it, we get the vectorial total variation energy. Finally, to generalize the previous two, if you replace the power with a variable p, you get the mixed norm energy. We'll discuss what each of these energies measure and what kind of crossfields they produce. What does the Dirichlet energy measure in a crossfield? Well, if you zoom in really close to the surface and you looked at just a pair of infinitesimally close frames, let's say that these frames differ in the normal direction by theta n, and they differ in the intrinsic twisting angle by theta t. Then what the Dirichlet energy measures is the squared sum of these angles, or in other words, the total angular difference. What's really interesting about this formula is that the theta n is uncoupled from theta t, which means a crossfield minimizing this energy is intrinsically smooth. It will be completely unaware of extrinsic properties of the domain. And to test this out, we have the following experiment. We took meshes of increasing resolution of essentially a cylindrical shell, just so it has very strong principal curvature directions, and attached to it a wedge of angle theta. And we forced the crossfield to align to the wedge angle, so that can be thought of as a boundary constraint. Then we solved for the Dirichlet energy minimizing crossfield to see how this boundary condition extends into the cylindrical region. As you increase the mesh resolution, the crossfield essentially maintains that wedge angle throughout the entire cylindrical piece. It is more or less unaware of the fact that this is a cylindrical shell and not a flat 2D surface. So this experimentally verifies that minimizing Dirichlet energy produces intrinsically smooth crossfields. Moving on to the total variation energy, which again is just when you don't square the integrand, we have to consider a very different setting. This is because total variation is designed to work well when you have piecewise constant functions with sharp discontinuities. In the crossfield setting, let's say we have a piecewise constant field on the three patches shown in blue. Let's call those patches omega. And the field is discontinuous on two curves gamma, marked in green. Then we can do integration by parts to decompose the total variation energy into the following two pieces. The first one measures smoothness on continuous patches. That is to say, if your crossfield had no discontinuities at all, then this term would essentially be the entire total variation. However, we also get the second term, which is a line integral over the discontinuity curves, and the integrand measures the difference between crosses on either side of the discontinuity, which we'll denote by f plus and f minus. Now it's worth looking closer at what the integrand of the line integral is in our representation, because this is what ultimately gives us the feature aligning property. So the integrand of the discontinuous jump part is just the L2 norm of the difference between the frames on either side. It turns out that on surfaces with creases, that's essentially a guaranteed discontinuity in the crossfield because the normal direction is discontinuous. And between the two patches, there is a feature curve running between them. If you try to minimize the energy minimizing configuration for the frames on either side has to be crease aligned, and so we'll call that automatic feature alignment. This is a property of the spherical harmonic representation, and as far as I know, hasn't been explored previously. To test this feature alignment energy term, let's take the domain we showed at the beginning, where extrinsic curvature and feature curves are contradicting. And if you were to minimize the total variation energy to obtain a crossfield, what you would get is the feature-aligned crossfield on the right. So now we'll talk about the mixed norm, where we replace the exponent with a variable p. We've already covered the p equals 1 and the p equals 2 cases, and in physics, once you've got 1 and 2, you might as well jump to infinity. This turns out to be difficult in the continuous setting, so we make one more simplification, which is that we're in the discrete setting. So now these are spherical harmonic frames on triangle faces of a mesh, and we're just measuring differences between frames that share an edge. Since the infinity norm is also known as the max norm, we can say that the mixed norm energy is measuring the maximum difference between any pair of adjacent frames. And if you look at what's inside of the maximization, it's actually the same as the feature aligning term that we talked about earlier. I think the picture to have in mind here is what would happen if every edge of your triangle mesh was considered to be a feature. Essentially, this energy is extremely sensitive to any sort of changes in normal direction of the mesh. So the mixed norm energies can be summarized as low values of P give lower feature alignment, while higher values of P give increasing feature alignment. Now let's talk about the results. One way to test this feature alignment idea is to use the Fandisk mesh, which is yet another example of where the extrinsic curvature of the underlying domain, shown in blue on the left, contradicts the directions of the feature curves, shown in red on the right. This Fandisk feature curve is notoriously hard to capture because that angle is extremely shallow. And as far as I'm aware, none of the previously existing crossfield algorithms would capture this feature curve. It would instead choose to pave over it as shown on the left, because that gives you a more intrinsically smooth field or a more extrinsic curvature aligned field. However, if you were to minimize the infinity norm energy, the crossfield you get is shown on the right and does align to that shallow crease much more closely. And if you were to compute quad meshes of these using either non-feature aligned crossfields, the p equals 2 energy or the p equals infinity energy, what you would get is quad meshes that are not feature aligned, slightly feature aligned, and more feature aligned. You might wonder what happens for the p equals 1 case. The funny thing is that even though I introduced feature alignment using the p equals 1 case, total variation weighs the feature alignment term against smoothness equally. This means the p equals 1 case usually doesn't align that well to feature curves since it has to balance against another smoothness term, whereas if you increase p towards infinity, you're really only concerned about the feature curves. Here's another example showing the p equals 1, 2, 4, and infinity crossfields computed on a mesh of an upper body. Focusing on the shoulder, you'll see that for low values of p, the crossfield treats the arm like it's just a cylinder. Towards p equals infinity, the crossfield starts to align to the muscle on the top of your shoulder. As soon as you increase sensitivity to features of a mesh, the crossfield manages to detect subtle muscle structure. While there's an infinite family of energies in our class, the minimizers don't always produce very different results. It really depends a lot on the base geometry, and so if you have a fairly smooth triangle mesh, the resulting crossfields can be pretty similar. We really have hundreds more experiments with large parameter sweeps and comparisons with many more previous works, but there are just too many to show. Instead, all of these experimental results, as well as code, can be found on our GitHub link. I hope some of you would be incentivized to take a look or try it out, and hopefully after this, you'll start to see that crossfields are everywhere. Thanks for listening.